Hello everyone, today we are going to talk about a novel multimodal fusion method for speaker recognition. Speaker recognition has been an active research area with applications in various fields, such as biometric authentication and security. The existing state-of-the-art model only uses a single modality, the audio features, to classify speakers. Therefore, we propose a multimodal fusion method which utilizes both audio and text features to perform robust speaker classification. Besides, we also work on a new dataset to validate our model performance. Our dataset includes about 1,400 entries with audio ground truth caption and speaker labels.
Okay, so here's the approach and methods part. In this part, we'll analyze our pipeline structure, and the structure here is composed of three parts. The first one is the pre-processing one. The second one is the analysis one. So in this third part, we have two different models to train and learn features. And the third one is the prediction part, where we fuse our output together and make a final output. So for the pre-processing parts, basically we use the same pre-processing part for both models. So here we cut the long complete audio to many small audio clips and then store them to the data loader as different trend and test data sets. And the below figure shows the procedure. So the first model in this part is the speaker recognition one. So it is basically built based on the SyncNet, and the input of it is just some audio clips. So given a second long audio, the model will convert it to multiple millisecond long frames. And in the last layer, the model will vote for the speaker with the highest probability among these frames. So the output is just the speaker class. In our case, it may be human voice, environment, or any other noises. So the total number of them is 99 in our case. And this model uses NLL as the loss function. The second model is the caption generation model. So it is basically built on the deep speech to model, and the input of it is little different. Its input is some audio waveform signal, and the model will convert it to a log spectrogram form. The output of it is just some speech text, and it needs to be noticed that we can only generate text from human speech instead of other environment or music noise. And this model uses CTC as the loss function. So once we got the caption from the last model, we can use that output to do the speaker recognition again. So as you can see, this model is text-based, and it is composed of 1D convolutional layer with other layers like pooling, dropout, and then batch normalization. So basically, this model takes the speech text, which generated from the audio as the input, and the output of the model is just the speaker class. And this model uses the cross-entropy loss.
To evaluate our model performance, we use Levenstein distance to evaluate the speech recognition model and use top-one classification accuracy to evaluate our speaker recognition model. Here are our experiment results. For speech recognition, we have compared deep speech 2 and fair sequence models. We can see that fair sequence has better performance because it uses attention-based RNNs. Besides, model trained on library speech datasets has better performance compared to KNNW because KNNW dataset is too small for the model to learn. And we also find that there is around 35% empty predicted sentence. And the main reason is that those sentences are more likely to be songs such as oh, or lyrics with background music. For speaker recognition model, we compare our MMSR model with two baselines, which use single modality. The audio-based approach achieves better performance because audio contains more meaningful information to distinguish different speakers, such as tone and timbre. When we combine audio and text features in our MMSR model, it can achieve better performance than any single branch. For the text branch of speaker recognition, we also explore the effectiveness using different model inputs. We can directly feed the model with ground truth text, and the result is shown in the first row. We can also use predicted text computed from fair sequence model. We can see that fair sequence brings errors to text prediction in the first stage, and it can lead to 3 points decreasing in the speaker classification accuracy on the test set. In conclusion, for a two-stage model, we need to guarantee the good performance of the first stage in order to have good final result. Second, in speaker recognition tasks, multimodal features can also improve model performance compared to single features.